Hello everyone. So in continuation with where we left off in class today, we're dealing with constraint optimization, and this video is going to go over a different method to solve constraint optimization problems. And this method is called the Lagrangian multiplier approach. So Lagrange is the person who is the mathematician who came up with this approach. So the method is named in his honor. So the goal is to optimize an objective function such as z is equal to f of xy, and it is subject to a constraint of this form, g of xy equals n. Now, the steps to go ahead and solve the problem using this method is first, we define a new function called the Lagrangian function, which is often written using this very fancy looking L that you see here. Now, the way you write this function, and this particular function is actually going to be a function of 3 inputs. So it's going to have x, y, and a new input called the lambda. So lambda is a Greek letter which looks like an inverted y, and lambda in this context is called the Lagrange multiplier. So the Lagrangian function is going to have all of these 3 inputs, and the way you write down the Lagrangian function is you first put down the objective function as it is, f of xy as it is. And then you do a plus lambda and you open brackets. And within the bracket, you put down the constraint in this particular form. So you have g of xy is equal to n right here. And you just move g of xy to this other side. You'll end up getting n minus g of xy. And that's what you will put here within the brackets right after the multiplier term. So f of xy plus lambda times the constraint written in this manner is your Lagrangian function. And you can see that it is now a function of 3 inputs, x, y, and lambda. The next step is once you have this Lagrangian function, you want to go ahead and take the partial derivatives of the Lagrangian with respect to each of the inputs, and you set it equal to 0. So this means you do dou L by dou x, first input, partial derivative, dou L by dou x, set it equal to 0. Dou L by dou y, where y is the second input, do dou L by dou y, set it equal to 0. Third input is lambda, do dou L by dou lambda, set that also equal to 0. And then you solve these 3 equations simultaneously. And the solution that you thus get, which is a set of points x, y, lambda, that will be your optimal solution to the constraint optimization problem. That is all you have to do. Write down the Lagrangian function and solve these 3 first order partial derivatives, and the solution you find happens to solve your constraint optimization problem, and you're done. So you can see here, right, when you have the first order partial derivatives, it's very similar to the case that we saw earlier on in the unconstrained optimization case, where you set the first fx equal to 0, fy equal to 0. And so it's very similar to that. You may ask me, hey, where are the second derivatives here? We did second derivatives in both the single and multivariable case when we were doing unconstrained optimization. Now, what's the deal? Where are the second derivatives? Well, it gets a little bit messy when you do second derivatives with Lagrangian. And for all practical purposes and for questions that you're likely to see in econ mostly going forward, the first derivatives, setting the first order derivatives equal to 0 is fairly good enough as a starting point. So we'll do just that and solve the Lagrangian function. I mean, we'll use the Lagrangian method to find optimal values. So I'm just going to go over an example really quickly. So let's use Lagrange multipliers to find the optimal value of this objective function subject to this constraint. So we have f of xy given to us directly. And to put the constraint in the form of g of xy equals n, so if you write down 2x plus 3y is equal to 6, now g of x is actually just 2x plus 3y, and m is just going to be 6. So when you want to write down the Lagrangian function, you put f of xy plus a lambda into m minus g of xy. And you will actually find out the value of lambda when you solve simultaneously in the next step. So put lambda as it is. So we have f of xy is just x square minus 3xy plus 12x, sorry, minus 3xy plus 12x plus a lambda into 6 minus 2x minus 3y. So this is my Lagrangian function, which is a function of x, y, and lambda. Now let's take the first order derivatives and solve simultaneously. So what will be the derivative of this function with respect to x, the partial derivative? So when you take the partial derivative, you keep y and lambda constant. So this is going to be 2x minus 3y plus 12 minus 2 lambda equals 0. So that's my dou L by dou x. Let me do dou L by dou y. And this is where I take the partial derivative with respect to y, and I'm going to keep x and lambda constant. So this will be minus 3x minus 3 lambda equals 0. Then the final one, dou L by dou lambda, so which is this variable you're interested in. And so treat x and y as constants, and you want to take the derivative with respect to lambda. And to make it easier for you, if you expand this term, you're actually going to get 6 lambda minus 2x lambda minus 3y lambda. So all you have to do is actually, when you take the derivative of L with partial derivative of L with respect to lambda, these are the set of terms you're focusing on. So what's your dou L by dou lambda going to be? It's going to be, so you treat x and y as constant and you're taking derivative with respect to lambda. So this is going to be 6 minus 2x minus 3y is actually 0. And if you rearrange, you're actually just going to get 6 is equal to 2x plus 3y, which is nothing but this is your constraint. So the partial derivative that you take with respect to the Lagrange multiplier, which will actually just give you back your constraint. Okay, so now we have these 3 equations and we have to solve them simultaneously. So I'm just going to put things in a slightly easy way. So let me just keep, okay, so we have x, y, and lambda. So we have 3 inequalities, 3 equations, and so it's going to be possible to find a solution. So the first step that I'm going to do is I'm actually just going to use this expression to get x in terms of lambda, all right? And then I'm just going to feed in the value of x in terms of lambda into each of the other 2 equations. And then you'll eventually end up getting an expression that is only in terms of y and lambda. Let's solve it. So you have minus 3x minus 3 lambda is 0. So minus 3x is equal to 3 lambda. So can I say x is equal to minus lambda? That is the first step. Right. So, okay, so you have x is equal to minus lambda. Right. And then let's plug in x is equal to minus lambda into the budget constraint. So you have 2x plus 3y equals 6. So this is just going to be minus 2 lambda plus 3y equals 6. When you plug in x is equal to minus lambda. Similarly, the first expression that we have here is 2x minus 3y. So I'm just taking this expression from here. So 2x minus 3y minus 2 lambda is equal to minus 12. So I'm going to plug in x is equal to minus lambda. So this is minus 2 lambda minus 3y minus 2 lambda is minus 12. So you get minus 4 lambda minus 3y is minus 12. So now you have 2 equations which are in terms of lambda and y, and we can solve them simultaneously to find lambda and y, right? So I'm just going to have minus 2 lambda plus 3y is 6, minus 4 lambda minus 3y is minus 12. And if I just add these 2 equations, then 3y and minus 3y will cancel out. So I'm left with minus 6 lambda is equal to minus 6. Therefore, lambda is equal to just 1. And when lambda is 1, x is equal to minus lambda, therefore x is equal to minus 1. And when you have x is equal to minus 1, you can plug this into the budget constraint and compute. But so 2x plus 3y is equal to 6. Therefore, 2 into minus 1 plus 3y is 6. 3y is just going to be 8. Therefore, y is equal to 8 by 3. And if you plug in x is equal to minus 1 and y is equal to 8 by 3, f of xy, the optimized value of the objective function is actually going to come to be, so you'll have to plug this into x square minus 3xy plus 12x. So which is minus 1 square plus 3 into minus 1 into 8 by 3 plus 12x, right? Which is 12 into minus 1. This is 1 minus 8 minus 12. So you get minus. Wait, I have messed up something. Oh, it's x square minus 3xy. So this will be plus 8. So you get 9 minus 12 minus 3. So that's your optimized value of the function. This is optimal value of f of xy. And your solution of x comma y comma lambda is minus 1 comma 8 by 3 comma 1. So, and that is all you need to solve the Lagrangian optimization problem. Now, I'm just going to leave you in this video with one thought. So remember, when you have your Lagrangian function written as f of xy, so okay, let me put it this way. So I have Lagrangian x comma y comma lambda is f of xy plus lambda into m minus g of x comma y. Now suppose we treat m as another variable. That is, you treat this m as another variable so that it becomes another input into your Lagrangian function. So your Lagrangian value now depends on 4 inputs, x, y, lambda, and m. Then, if you take the first derivative of the Lagrangian function with respect to m, what do you get? You get lambda. So the Lagrangian function pretty much becomes our main function of interest here when we do the constraint optimization in this method. So, and when you take the derivative of Lagrange with respect to your m, which actually defines your constraint, then that is going to be equal to lambda. And I'm going to leave you with that, with just that result in mind. And in a subsequent video, I will go over an econ-based example, the one that you see right down here. And we'll see what role that particular lambda plays and the economic role of that lambda in the particular example. So I will see you in another video.